Right now, as you are watching this, you are spinning. Not just because Earth turns on its axis, not just because Earth circles the sun. You are spinning because everything spins. Your galaxy spins. The group of galaxies you live in spins. Even the giant walls of galaxies that stretch across the universe, those spin too. This is not theory. This is measured fact. And for nearly 100 years, we have been trying to understand why. Because according to everything we know about how the universe began, this should be impossible. The Big Bang should have created a universe that does not spin at all. A universe where matter spreads out equally in all directions, like a ball growing bigger and bigger. No turning, no twisting, just pure growth outward. But that is not what we see. Everywhere we look, we find rotation. Planets spin, stars spin. Galaxies spin so fast that they should tear themselves apart, yet something holds them together. Galaxy groups orbit around invisible centers. Even the largest structures we can see, walls of galaxies billions of light years long, they carry a hidden twist in their shape. The numbers are clear, the measurements are solid, and they tell us something shocking. The universe has a spin we cannot explain. This breaks our models. It shatters the smooth, simple picture of cosmic growth we built over decades. And what makes this truly strange is that we only discovered it recently, not because the spin is small, but because we were not looking for it. We assumed it could not be there. Think about that for a moment. We missed one of the most basic features of the cosmos, because our equations said it should not exist. But the universe does not care what our equations say. It spins anyway. And now we must face a choice. Either everything we know about the Big Bang is wrong, or something happened in those first moments, something we do not understand, that set the entire universe turning. This is not a small problem. This is a crisis at the foundation of cosmology, and it demands an answer. When scientists first started mapping the universe beyond our own galaxy, they expected chaos. They thought galaxies would be scattered randomly across space like dust thrown into the air. But that is not what they found. In the early decades of the 20th century, astronomers began taking pictures of distant galaxies. They measured how fast these galaxies were moving. They tracked their positions over years, and slowly a pattern emerged. Galaxies were not scattered. They were organized. They grouped together in clusters. These clusters themselves grouped into even larger structures, and all of it was moving. Not just expanding with the universe, but moving in specific directions, with specific speeds. By the middle of the century, we knew galaxies rotated. We could measure their spin by watching how light changed as one side moved toward us and the other moved away. Every spiral galaxy we looked at was turning, some faster, some slower, but all spinning around a center. This made sense. Gravity pulls matter together. As matter collapses into a smaller space, it spins faster, just like an ice skater pulling in their arms. We called this conservation of angular momentum. It is a law of physics, as solid as any we know. So galaxies spin. Fine. But then we zoomed out. We started looking at groups of galaxies, and we found something unexpected. These groups were spinning too. Not as fast as individual galaxies, but the motion was there. Galaxies within a cluster were not just held together by gravity. They were orbiting, moving in paths around a common center, like planets around a star, but on a scale millions of times larger. This was harder to explain. When the Big Bang happened, it should have created matter that spreads out smoothly in all directions. Imagine dropping a stone into a perfectly still pond. The ripples spread outward in circles, equal in all directions. That is what the Big Bang should have done. No rotation, no twist, just growth. But here we were, finding rotation everywhere. At first, scientists said this was okay. Maybe small, Random differences in the early universe created tiny spins. As gravity pulled matter together, these tiny spins grew larger. A small twist in one region becomes a rotating galaxy cluster billions of years later. The math worked. The explanation fit. We moved on. But we should not have. Because the problem was much bigger than anyone realized. In 2020, a team of researchers did something simple. They looked at the shapes of galaxy filaments. These are the largest structures in the universe. Imagine the cosmos as a giant spider web. Galaxies sit along the threads. Between the threads is empty space, huge voids, where almost nothing exists. These threads, we call them filaments, stretch for hundreds of millions of light years. They contain thousands of galaxies. They are the skeleton of the universe. The researchers measured how these filaments were aligned. They checked the angles. They looked at how the galaxies inside were moving, and they found a pattern. The filaments were not just sitting there. They were twisted, not randomly, not by chance. There was a clear, measurable corkscrew shape to how matter was arranged. This was not the spin of a single galaxy. This was not even the spin of a galaxy cluster. This was rotation on a cosmic scale, affecting structures so large that light takes hundreds of millions of years to cross them. The paper was published. The data was checked. Other teams looked at different parts of the sky. They found the same thing. The universe had a twist to it, a rotation that existed on the largest scales we could measure, and this should not be possible. Let me be clear about why. When we model the Big Bang, we start with a few basic rules. The universe begins as a single point. It explodes outward. Matter and energy spread in all directions equally. Tiny random differences, quantum fluctuations, create small clumps. These clumps grow because of gravity. Over billions of years, they become stars, galaxies, clusters, filaments. At no point in this model does large-scale rotation appear. You cannot get a spinning universe from a non-spinning Big Bang. The math does not allow it. Conservation of angular momentum says that if the universe starts with zero spin, it must always have zero spin overall. Individual parts can spin, yes, but they must spin in random directions, some clockwise, some counterclockwise. When you add them all up, the total should be zero. But what we observe is not random. The spin has a direction, a preference. When researchers measured the twist in those cosmic filaments, they found that more of them twisted one way than the other, not by a huge amount, but enough to be real, enough to be measured, enough to break the rules. This is not a small correction to our models. This is a fundamental problem. It means either our measurements are wrong, which seems unlikely given how many teams have now confirmed this, or our understanding of the Big Bang is incomplete. Something is missing from the picture, something we have not accounted for. And the clock is ticking to figure out what. Let us step back and talk about what spin actually means on cosmic scales. When we say the universe spins, we are not saying it rotates like a ball. The universe has no edge, no outside. There is no fixed point to spin around. Instead, what we mean is this. Take any large region of space. Measure how matter is moving inside it. If there is rotation, you will find that on average, matter prefers to move in a certain direction. Clockwise or counterclockwise, depending on your view. This preferred direction is what we call cosmic angular momentum. To understand why this is strange, imagine you are in a room with 100 people. You ask each person to spin in place, whichever direction they choose. Some will spin left, some will spin right. If you add up all their spins, the total should be close to zero because half go one way and half go the other. Now imagine instead that 70 people spin left and 30 spin right. That is weird. That suggests something made them choose. Some force, some instruction, some starting condition that pushed the group toward one direction. That is what we see in the universe. Galaxies, clusters, filaments, they all spin. And when we add them up, we get a number that is not zero. The universe has a net spin, a preferred rotation, and we have no explanation for where it came from. Scientists have tried to explain this in different ways. One idea is called tidal torque theory. It says that as matter collapses under gravity, nearby clumps of matter pull on it unevenly. This creates a twist, a torque, that makes the collapsing region start to spin. The math works for individual galaxies. We can explain why a galaxy spins by looking at the galaxies around it. But this does not explain large-scale rotation. Tidal torques average out over big distances. You cannot use them to make the whole universe spin in one direction. Another idea is that the universe never actually had zero spin. Maybe the Big Bang itself was rotating. Maybe the very first moment of existence had a twist built into it. This sounds good until you think about what it means. If the Big Bang was spinning, then we need to explain why. What made it spin? Where did that angular momentum come from? And this just pushes the problem back one step. We have not solved anything. We have just moved the mystery to an earlier time. A third idea, and this one is more radical, is that our picture of the Big Bang is wrong. Not completely wrong, but missing something important. Maybe there was a phase before the Big Bang we do not understand. Maybe there are forces or fields we have not discovered yet that can create rotation on large scales. Maybe the smooth, simple expansion we imagine is not what really happened. This is where things get uncomfortable. Because if the Big Bang model is incomplete, then so is everything built on top of it. Our timeline of cosmic history, our understanding of dark matter and dark energy, our predictions about the universe's future, all of it rests on the idea that the Big Bang was smooth and symmetrical, but the spin says it was not. Now we must look at the evidence in detail, because when you make a claim this big, you need data that cannot be argued with. The first clue came from looking at galaxy spins individually. In 2011, a study looked at more than 15,000 spiral galaxies. They checked which direction each galaxy was spinning. If there was no cosmic rotation, you would expect half to spin clockwise and half counterclockwise, depending on your viewing angle. But that is not what they found. There was a small but clear difference. More galaxies spun one way than the other. The difference was only a few percent, but with 15,000 galaxies, that is statistically impossible to ignore. It was real. Then in 2020, the filament study came out. This time, researchers used data from huge surveys that mapped millions of galaxies. They looked at the three-dimensional shapes of cosmic filaments. They measured angles, distances, velocities, and they found the corkscrew pattern. The filaments were twisted, not all of them, but more than random chance would allow. The twist had a direction, a handedness, like a screw that turns clockwise instead of counterclockwise. Other teams checked this using different methods. Some looked at the polarization of light from the cosmic microwave background, the leftover glow from the Big Bang. They found hints of rotation there too. Others studied the flow of galaxies, the way they move through space in large groups. Again, a preferred direction showed up. By 2023, the evidence was piling up. Different measurements, different methods, different parts of the sky, all pointing to the same conclusion. The universe has a net angular momentum, a spin that should not be there. But here is where it gets tricky. The size of the spin is small, very small. If you measure the rotation speed at the edge of the observable universe, it comes out to less than 1 rotation per trillion years. That is incredibly slow. But it is not zero. And zero is what our models predict. So even a tiny spin is a huge problem. Some scientists argue the measurements might be wrong. Maybe there is a bias in how we select galaxies to study. Maybe the instruments have a systematic error we have not noticed. Maybe the statistical methods are flawed. These are fair questions. Science demands skepticism. But here's the thing. Multiple teams using different telescopes, different data sets, different analysis techniques are all finding the same signal. At some point, you have to accept that the signal is real, that the universe is telling us something we do not want to hear. Our models are incomplete. So what could cause a spinning universe? Let us explore the possibilities, even the wild ones. The first option is primordial rotation. This means the universe was born spinning. The Big Bang itself had angular momentum from the very start. But where would that come from? One idea involves something called quantum fluctuations. In the very first moments after the Big Bang, the universe was incredibly small, smaller than an atom. At that scale, quantum mechanics rules, and quantum mechanics allows for random fluctuations in every property, including angular momentum. Maybe just by chance, the universe got a tiny spin from these quantum jitters. As the universe expanded, that tiny spin got stretched out across space. It became the large-scale rotation we see today. The problem with this idea is the numbers do not add up. Quantum fluctuations should create rotations in all directions equally. You would get some regions spinning clockwise and some counterclockwise, averaging to zero. To get a net spin, you need something to break the symmetry, something that prefers one direction over another. And we do not know what that something could be. A second option is cosmic strings. These are theoretical objects, incredibly thin, but incredibly dense lines of energy left over from the early universe. If they exist, cosmic strings could stretch across the cosmos. And if these strings were moving or vibrating, they could drag space itself along with them, creating rotation. This is speculative. We have never detected a cosmic string. But if they are real, and if they are arranged in the right pattern, they could twist the universe as it grows. The rotation would build up over time, creating the pattern we see. A third option is something called frame dragging. This comes from Einstein's general relativity. The idea is that rotating mass drags space around it. You see this near spinning black holes. Space itself swirls like water going down a drain. Now imagine this on a cosmic scale. If there was something massive and rotating in the early universe, it could have dragged the entire universe into a spin. But what could be massive enough to do this? We do not know. Maybe a spinning black hole at the center of the cosmos? But the universe has no center. Maybe some exotic matter we have not discovered? Maybe. But again, this is speculation. A fourth option, and this is the most disturbing one, is that the Big Bang was not the beginning. Maybe there was something before, another universe perhaps, that collapsed and then bounced back. If that earlier universe was spinning, then our universe inherited that spin. This is called a cyclic cosmology. The universe goes through endless cycles of expansion and collapse. Each cycle passes some properties onto the next, including angular momentum. The problem is we have no evidence for this. None. It fits the data, but so do 100 other wild ideas. Without a way to test it, it remains just an interesting story. Here is what makes this mystery so hard to solve. We cannot go back in time. We cannot watch the Big Bang happen. All we can do is look at the universe today and try to work backward. It is like finding footprints in the sand and trying to figure out what kind of animal made them, how fast it was moving, and where it was going. You can make guesses, but you cannot be sure. The cosmic microwave background is our best window into the early universe. This is light that has been traveling through space for more than 13 billion years. It shows us what the universe looked like when it was only 300,000 years old. Scientists have studied this light in incredible detail. They have mapped tiny temperature differences across the sky. They have measured how the light is polarized, twisted as it travels. And they have found something interesting. There are patterns in the cosmic microwave background that hint at rotation. Not strong, but they are there. The patterns are subtle. They show up as slight correlations in how the light is oriented in different parts of the sky. If the universe was perfectly symmetric, these correlations would not exist, but they do. This suggests that even in the early universe, there was already some rotation built in, but the rotation was so small back then that it barely showed up. Over billions of years, as gravity pulled matter together, the rotation grew. Small twists became big twists. Tiny spins became galaxy clusters orbiting around each other. And now, 13 billion years later, we can finally measure it. But measuring it is not the same as understanding it. We know the spin is there. We know it grew over time. We know it should not exist according to our models. What we do not know is what started it, what broke the symmetry, what gave the universe that first tiny push into rotation. Some scientists think the answer lies in the physics of the very early universe. In the first fraction of a second after the Big Bang, the universe went through a phase called inflation. This was a period of incredibly fast expansion. Space grew faster than the speed of light. This solved a lot of problems in cosmology, like why the universe looks the same in all directions. But maybe inflation did more than just smooth things out. Maybe it also created tiny rotations. If the field that drove inflation had some twist to it, some asymmetry, then that twist could have been imprinted on the universe, and as space expanded, the twist would have been stretched across the cosmos. This is just a theory. We have no direct proof that this happened, but it fits the pattern. It gives us a mechanism, a way for rotation to be created in the early universe without violating any laws of physics. The problem is testing it. Inflation happened so long ago, in such extreme conditions, that we cannot recreate it in a lab. We have to rely on observations. And observations are tricky. Let us talk about scale again, because this is crucial to understanding why this mystery is so profound. When we look at a single galaxy, the spin makes sense. Matter collapses. It speeds up. It forms a rotating disk. We see this happening. We can model it, no mystery. When we look at a galaxy cluster, the spin is harder to explain but still manageable. Maybe gravitational interactions between galaxies create the rotation. Maybe the cluster formed from a region that already had a tiny spin. We can imagine ways for this to happen. But when we look at cosmic filaments, structures hundreds of millions of light years across, the spin becomes impossible to ignore. These structures are so large that they formed very early in cosmic history. They are fossils of the early universe, and they are twisted. This is not something that happened over time. This is not the result of galaxies bumping into each other or gravity pulling things around. This twist was baked in from the beginning. It is a signature of the conditions in the early universe, and those conditions, according to our models, should not include rotation. The universe should be isotropic, the same in all directions. It should be homogeneous, the same at all locations. These are the two pillars of modern cosmology. If you drop these assumptions, everything falls apart. But the rotation suggests they are not quite true. The universe is almost isotropic, almost homogeneous, but not perfectly. There is a tiny deviation, a tiny preference for one direction over another. And that deviation is enough to create the spin we see. Now think about what this means for our place in the cosmos. We live inside a spinning universe. Everything around us is turning. The galaxy we live in, the group of galaxies around us, the filament we belong to, all of it carrying a motion that traces back to the first moments of existence. You cannot feel it. The spin is far too slow, but it is there, a hidden current in the fabric of space itself, and we are riding it, whether we know it or not. This is not just a curiosity. This is a clue to what happened in the beginning, a clue to forces and fields we have not discovered, a clue to a deeper layer of reality that our current theories do not capture. And if we can figure out what causes this spin, we will have unlocked one of the universe's deepest secrets. The implications of a spinning universe go far beyond just cosmology. They touch on some of the biggest questions in physics. Let us start with dark matter. We know that most of the matter in the universe is invisible. It does not give off light. It does not interact with normal matter except through gravity. We call it dark matter, and it makes up about 85% of all matter. We detect dark matter by watching how galaxies move. Galaxies spin so fast that the stars inside should fly apart, but they do not. Something invisible is holding them together. That something is dark matter. Now here is the question. Does dark matter spin? If the universe has a net rotation, then dark matter must be part of it. Dark matter is most of the mass in the universe. If it was not spinning along with everything else, we would see a difference between how visible matter moves and how the overall gravity behaves. But we do not see that difference. This means dark matter is spinning too. And that gives us a new way to study it. If we can measure the rotation of dark matter directly, we might be able to figure out what it is. Different theories of dark matter predict different behaviors. Some say dark matter is made of particles that barely interact with anything. Others say it is something more exotic, like microscopic black holes or ripples in extra dimensions. Each theory makes different predictions about how dark matter would rotate. By studying cosmic rotation, we can test these theories. We can narrow down what dark matter could be. This is huge. Dark matter is one of the biggest unsolved problems in physics. Any new tool to study it is valuable. Now consider dark energy. This is the mysterious force that is making the universe expand faster and faster. We do not know what it is. We just know it is there, pushing everything apart. Some scientists think dark energy might be related to rotation. Maybe the spin of the universe creates a kind of tension in space, and that tension is what we call dark energy. This is speculative, but it is worth exploring. If rotation and dark energy are connected, then understanding one might help us understand the other. And finally, there is the question of cosmic symmetry. Physics is built on symmetries. The laws of physics should be the same everywhere and at all times. If you do an experiment here on Earth and then do the same experiment on the other side of the universe, you should get the same result. This is called the cosmological principle. But a spinning universe breaks this symmetry. A spinning universe has a preferred direction, a handedness. This means the laws of physics might look slightly different depending on where you are and which way you are facing. The differences would be tiny. We would not notice them in everyday life. But on cosmic scales, they could add up. They could affect how galaxies form, how structure grows, how the universe evolves. And if the laws of physics are not perfectly symmetric, then we need to figure out why. What is breaking the symmetry? Is it something fundamental about the universe, or is it just a historical accident, a random fluctuation that happened to go one way instead of another? We are living in a strange moment in the history of science. For the first time, we have the tools to measure the universe on the largest scales. We have telescopes that can see billions of light years away. We have computers that can process data from millions of galaxies. We have mathematical models that can simulate the entire universe from the Big Bang to today. And with these tools, we are finding things we did not expect. The universe is not as simple as we thought. It is not as smooth, not as symmetric, not as predictable. It has quirks, twists, mysteries. The rotation is just one of them, but it might be the key to unlocking the others. Because if we can figure out why the universe spins, we will have learned something deep about how it began. We will have glimpsed the conditions in those first moments. We will have seen the fingerprints of forces and fields that no longer exist, or that we have not yet discovered. This is the promise of modern cosmology. not just to map the universe, but to understand it, to read its history written in the patterns of galaxies, to decode its secrets hidden in the motion of matter. The spin is one of those secrets, and we are closer than ever to cracking it. But we are not there yet. We need more data, more observations, more theories. The next generation of telescopes will help. Projects like the Vera Rubin Observatory will map tens of millions of galaxies. The James Webb Space Telescope is already looking back to the earliest galaxies, the first structures that formed. The Euclid mission is measuring the shapes and positions of billions of galaxies across half the sky. All of this data will help us understand the rotation. We will measure it more precisely. We will see if it changes over time. We will track how it affects the growth of structure. And slowly, piece by piece, we will build a new picture of the universe. A picture that includes rotation. A picture that explains where it came from and what it means. This will not happen overnight. Science moves slowly, carefully. We test ideas, we check results, we argue and debate. But eventually, we figure things out. We always do. The universe spins, and soon we will know why.